Yeah, the previous videos were centered around introductions to decision trees and recursive algorithms, and now we are going to talk about different types of decision trees. So basically how we can alter certain design choices and end up with different implementation of decision tree algorithms. But first, let's briefly recap the generic decision tree algorithm in pseudocode here. That is from the previous video. I just wanted to briefly recall certain aspects here. So in particular, this was a binary classification problem because we had only class labels 1 and 0 that we considered here. And we also talked about a binary tree, so basically binary splitting. And that was related to the fact that we split each node into only 2 child nodes. If we have one node, we always split into 2 subnodes. And then there was another binary thing here, and that was binary features. So here we also only considered binary features, so that means feature values where the possible values can only be 0 and 1. However, based on what I've shown you earlier in the context of scikit-learn, the decision tree visualization, we can also use continuous features and convert them to binary splits. For example, if we pick a given feature, xj, then we can split it in 2 parts. For example, we can set a threshold here, and then we can say xj smaller than t, or xj greater or equal to t, and we can use that as a decision criterion. For example, can use xj greater or equal to t, and then we can set it true or false here. In that way, it would be also a binary split, and in contrast to using a binary feature, this would be still a continuous features, because as part of finding the split, I can move the decision threshold left and right, and we will do that in the homework. So in the homework, we will implement a decision tree algorithm. Already almost finished making the homework. We will be using the so-called card algorithm, and at each node in the decision tree, we'll consider one feature. So we have a feature xj, where j is a value between 1 and m, so we have up to m features. And at each node, here, let's say at each parent node, when we split the parent node into child node, let's say child 0 and child 1, like here, what we have to do is we have to consider which feature to choose, which one here, and also for then, if that's a continuous feature, we have to consider the decision threshold, where the threshold is. Or in particular, there will be choices like is x2 greater equal to, let's say, 2.3 centimeters in terms of sepal length in the iris dataset. Is that a better splitting criterion than, let's say, x3 greater or equal to 5 centimeter? So which one of the two is better? And for that we will need a measure of goodness, how we measure how good a split is. So just to summarize the generic tree algorithm in pseudocode, so what we have, just to summarize the generic tree growing algorithm in pseudocode, just to summarize the generic tree growing algorithm in words. So what we do is we pick the feature that when the parent node is split, so when we split the parent into 2 child nodes, it results in the largest information gain. And information gain is our measure for goodness of split. So the greater the information gain, the better the split, or the better the feature given its splitting threshold for a continuous feature. And how we measure that, there are 2 measures. One is entropy and one is Gini. There are of course more than these 2 measures, but these are the most popular ones, and we will talk about that about these 2 in the next video. Then here at part 2, The stopping criterion then is stop if child nodes are pure or the information gain is smaller or equal to 0. That means if we don't make an improvement, so this part means if we don't make an improvement, then stop, or if the child nodes are already pure, then also stop. So pure means if we have a node where all the corresponding data points have the same class label. So when we start growing the decision tree, we have the whole data set here, and then every time we split, we have a subset. So here we have D0 and here we have D1. So it's a subset of the data set, and each data set subset consists of pairs of features and the corresponding class labels in the training set. So we have, let's say, data point 1 and 1 up to, for this node, up to, let's say, n. So we have a number of data points, and if all of them correspond to the same class label, so that is if this class label is 1 and all the other ones are 1, then the child node is pure, so there's no mix in labels. However, if some of them are 0, then this is not a pure node. So let's say we have 3 1s and 1 0 here as the class label. In that case, the node is not pure. And the third step then would be go back to step 1 for each of the 2 child nodes, but again, for the given node we stop if the node is either pure, so if all of them have the same label, or if they don't have the same label, if they are not pure, but we don't make any information gain progress here. That would be another stopping criterion. So there are 2 criteria here. They are a little bit related, because if the nodes are already pure, we also have a 0 information gain. Now suppose we grew the tree, we finished the growing, so this one is finished, and we want to make predictions now. So after growing, let's say we have a tree like that. It doesn't have to be a balanced tree, so that is our decision tree here. And let's say here are all the training examples from class 1. Here we have some class 1 examples and let's say class 0 example, and here we have all class 0 examples. So the original data set at the parent node would have been 1, 2, 3, 4, 5, 6, 1, 2, 3, 4. So these would be the class labels at the parent node. And then we split it such that 3 of the ones ended up here and the other 3 ended up here. So that means at this node here, what we had was 1, 2, 3, 1, 2, 3, 4. And these were then again, let's say, split into this one, which belongs to this one, and these 3 here. Yeah, and note that these are the class labels that we are talking about here. So for example, at the root node here, we could have, for example, had a splitting criterion like x2 greater or equal to 2 centimeters or something like that, if we talk about sepal dimensions, and or this is, let's say, the petal length. And then here we could have maybe petal width greater or equal to, I don't know, say 3 centimeters. I'm just making these numbers up. We will work with the iris dataset in the homework, so we will see the actual numbers then. So we have 2 splitting nodes. One is this one here. So let me use maybe a different color. Which color didn't? So maybe this yellow one. So I haven't used yellow here yet. So this would be corresponding to this one. And this is, this is way too messy. Let me erase this. So let me do, for this node here, x2 greater or equal to 2 centimeters. And then for the second node, x3 greater or equal to 3 centimeters. So here we have one splitting happening, and here we have one splitting happening. So if we have a new training example, let's call it x new, or not training example, just a new data point, for which we want to predict the label. Now for these we have the feature values, let's say 1 centimeter, 1 centimeter, 1 centimeter, and 1 centimeter to keep it simple. So all the feature measurements are 1 centimeter, where this is x0, the first feature, this is x1, the second feature, this is x2, the third feature, and this is x3, the fourth feature. Now if I have a data point like that, I want to make a prediction. I go to this first node here, I check, okay, x2 greater or equal to 2 centimeters. To the right hand side I have a true, and to the left hand side I have a false. It is not greater than 2 centimeters, right, because here I have 1 centimeter, so I would go to the left here. And then the next question is x3 greater than 3 centimeters? If I look at this value here, again, this is not greater than 3 centimeters. Let's say the left hand side is false and the right hand side is true. So again, would go here to the left hand side. Now I'm at this node and I have to make a prediction for the class label for that one. So how do I make my prediction now that I have a node that is not pure? So in this case, we can use the majority vote that we also used for the k-nearest neighbor classifier. So we can just compute the mode or majority vote here of the most frequent class. So the most frequent class would be our majority vote, which would be the prediction. So in this case, predict class label 1. Note also that this of course also works for more than 2 classes. In the pseudocode on the previous slide we had a binary classification problem, but this works with an arbitrary number of class labels, so we could also have some class labels 2 here at this node, so we would also have some 2's here, maybe 1 2 ends up here. So this doesn't really matter whether we have a binary classification or a multi-class classification problem. In both cases, yeah, this decision tree would work the same way that we do the majority vote here at the leaf nodes. And I hope this will also become more clear when you work on the homework, where we will implement such a decision tree from scratch. Now, there are different design choices that we can make when we develop decision tree algorithms. And one design question is centered around the question, how do we split? So a sub-question for that would be, what is the criterion for splitting a node? How do we measure or how do we compare different splits to find out what a good split is? And in the next video we will talk about 2 different measures, entropy and Gini impurity, for measuring the goodness of the split. The second question is related to whether we should use a binary or multi-category split. So consider a case where we have a feature column with more than 2 possible values that are categorical. For example, let's say we have feature xj and the possible values are red, blue, green. For that we can develop a decision tree with a multi-category split. For example, let's say this is the parent node, and then we can, based on the feature value, split it into 3 child nodes, like red, blue, and green, right? So here this would be xj equals red, and here it would be xj equals blue, and here it would be xj equals green. However, we could write the same tree using binary splits. For example, we can write it as follows. We can convert this feature, this categorical feature, into one-hot encoding, right? So we saw one-hot encoding in the previous week. So we can write this as follows. We have a new feature, we call that feature xred, which can be either equal to 1 or equal to 0. So we use first the feature xred as our criterion. And then we say, let's use a different color here. Then we say it's equal to 1 or equal to 0. If it's equal to 1, then these are all our red data points. If it's not equal to 1, if it's equal to 0, then we have here the blue and the green data points. And then we can split them further. We can now either use blue or green. So let's say we use blue. So we can say x blue. If this equals to 1, then put the child nodes here, or the data points into this child node. And otherwise, if this is 0, then put the data points here. So if I have a data point that is neither red nor blue, then it must be green, right? So we have all the green ones here, all the blue ones here, and then the red ones here. So this binary decision tree would be equivalent to this multi-category decision tree. However, while we can represent each multi-category decision tree via binary decision trees, when we use a decision tree algorithm for binary splits, it doesn't really mean that it will turn out the same way as the multi-category one. With that I mean, for example, if you have a data set with multiple features, let's say this was xj, the one with the color, and then we have also xp and xq or something like that. When we converted this multi-category tree into this binary tree on the right hand side, it was only converting the xj column into a one-hot encoding, and then we were using on this side here all the xj related new features. With that I mean we use then x red and x blue, right? However, in practice what could happen is that we first split on x red here, but then let's say instead of continuing with x blue, the algorithm will find it will use xp now. And then, so first we will use what I mean is x red, then xp, and then x blue again, and so forth. Especially if we have feature categories with many possible values, in practice, converting them to one-hot encoding and doing binary decision trees can really bias the data set towards these one-hot encoded features. And yeah, so in practice though, it's usually easier to implement decision trees using binary splits, because when we have continuous features, it's way easier to find a good threshold, right? Consider a case where we have the iris sepal length, and we want to find a threshold. Let's say the values are between 0 and 10 centimeters. If we only do a binary split, we only have to find one value here as a threshold. If we do a multi-category split, we have to first determine how many thresholds do we use, and then also where to place the thresholds with respect to each other. And this is computationally very expensive to evaluate what would make a good split, so the number of thresholds and distance of these thresholds to each other. So in practice, when we have continuous features, it's way easier to work with binary decision trees. Okay, and now another question is when to stop growing a decision tree. We said in the previous slide, one condition could be if the leaf nodes contain only examples of the same class, so if they are pure. Or we can also say if all the feature values for all the examples at a node are the same, so in that way there's no way that we can define new decision rules. That could also be one criterion to stop. And another one would be using a statistical significance test to see whether splitting a node significantly improves the information gain. So there are multiple questions to ask ourselves when designing algorithms. One is related to how we split a decision tree or decision tree node, and one is related to when do we stop growing a decision tree. And in the next slides I will show you some algorithms that make different design choices. So one of the earlier decision tree algorithms is the so-called ID3 algorithm, which was developed by Quinlan in 1986. The ID3 algorithm cannot handle numeric features, unfortunately. So if you have a continuous value like sepal length, this one wouldn't work. It can only work with discrete features, which can be binary or multi-category features. Also, this algorithm doesn't support pruning, which can make the decision tree prone to overfitting. What's also notable is that this algorithm produces short and wide trees, and that's a side effect of the multi-category splits. So if you have a given parent node and you have a feature for splitting that has many different feature values, what it can do is what it will do is it will then produce a lot of child nodes, right? So in this way, if you have these multi-category features and each one has a lot of child nodes, you will have this rather short and wide tree. If you only have binary splits in comparison, you would more like end up with long and narrow trees because you can only have 2 nodes, right? So you would have more like these deep and narrow trees, whereas with multi-category splits you have like these short and wide trees. I'm not saying short and wide trees are bad, it's just like in comparison to other binary algorithms, it's producing short and wide trees. And how it is deciding which feature to use for splitting, and how is it evaluating the splits? So this algorithm is maximizing information gain by minimizing entropy, and we will talk about entropy in the next video. Another algorithm is the C4.5 algorithm, which supports both continuous and discrete features. It was also developed by Quinlan in 1993. And while it supports the continuous features, we shall note it's very expensive because, like I said, if we have a continuous feature where we have a continuous number scale, it would be very expensive to find out what is a good feature. So we have an arbitrary number of thresholds, and then we have to define the distance between the thresholds, i.e. the intervals, and that can be relatively expensive. Anyways, an advantage of the C4.5 algorithm is that it can handle missing attributes. So this would be an algorithm where we don't have to worry about NANDs, like the NANs in our dataset. And it also performs post-pruning, so once the decision tree is built, so once you have a decision tree, it will take a look at the tree after building it and then remove certain nodes to make to improve the validation set performance, to reduce overfitting. So it may find, okay, this is too much here, so it may so if we have another level, so it may find this is too deep here, and it may find that removing this node and merging it into one node, merging it back by one level, will improve the validation set performance. And that would be the post-pruning, and we will talk about post-pruning also in a later video, how that works exactly. And for growing the tree, it uses the gain ratio. Instead of entropy, it uses the gain ratio to grow the tree, and we will also define the gain ratio in more detail later on. So we are only looking at short overviews of the different algorithms here. Just want to highlight that there are different algorithms, and we will discuss certain aspects of these algorithms later on. And one of the most popular algorithms is the CART algorithm by Leo Breiman, and CART stands for classification and regression trees. So you have the CART here. So this one, similar to C4.5, also supports continuous and discrete features. However, in contrast to C4.5, it only produces strictly binary splits. Consequently, the trees from CART will be taller than ID3 of C4.5 trees. Like I said before, if you have these binary splits, the trees will be deeper and narrower, or taller, so where taller means deeper, than C4.5 trees, which can have more than 2 child nodes per parent node. So here usually end up with these wider trees in the C4.5. And it uses the Gini impurity for evaluating splits in the context of classification, which also is called the Turing criteria. We will talk about Gini impurity also later in a later video, next video actually. And the CART algorithm also works for regression. So it supports regression trees, which is where the name here comes from. And in order to do that, it does variance reduction. We will also take a look at this in a later video. And variance reduction, in short, refers to the variance of the target variable. So it will reduce the variance of the target variable at each node, which is in a sense, can be shown it's equal to minimizing the mean squared error. And it also supports pruning. And in particular, the method is called cost complexity pruning. And this is not implemented in scikit-learn yet. Scikit-learn implements something like CART, but it doesn't implement the cost complexity pruning. In any case, CART is still the most widely used decision tree algorithm. And there are also several other decision tree algorithms. One is the chi-squared automatic interaction detector, which was developed in 1980. And if I remember correctly, this one is based on performing a chi-square test at the nodes to see whether its split is significant, statistically significant. So it will kind of only perform a split if you have a significant improvement. And there is also MARS, which stands for Multivariate Adaptive Regression Splines. And another one would be the C4.5 algorithm, which is like the successor of the 4.5 algorithm, the C4.5 algorithm. However, this one is patented. But yeah, there are many different algorithms. So we will discuss certain aspects from mostly CART and ID3 and also C4.5 in the context of the next couple of slides. So the next in the next video I will talk about entropy, which is implemented in ID3. So we will talk about entropy, and we will talk about Gini impurity. Again, scikit-learn, we will see that later, implements something like CART, where we can do binary splits, supporting continuous and discrete features. However, it allows us to choose the optimization metric, so in that way it's also borrowing some ideas from ID3 using the entropy. But yeah, so it's not a very strict implementation of CART. It's a CART with some more bells and whistles, I would say. And we will see that also later when I show you the code examples. But yeah, next video I will talk about the splitting criteria, entropy, and Gini impurity.